Have you ever wondered what the real difference is between homing and referencing an axis? Let's break it down, step by step. In general, both homing and referencing are used to establish a known relationship between the mechanical position of an axis and its logical position in the controller. But they do this in two very different ways. When we talk about homing an axis, we mean that the motor encoder aligns itself to a known mechanical reference by physically moving the axis. The axis moves until it reaches a machine reference position, which is usually detected by a sensor, like a limit switch. This approach is typically used with servo motors that have incremental encoders, because incremental encoders don't know their absolute position after power-up. Referencing, on the other hand, works differently. Here, the controller simply accepts the absolute mechanical position provided by the encoder and assigns that position to its logical coordinate system. No axis movement is required. This is possible when you're using a servo motor with an absolute encoder. To demonstrate this, let's take a look at our test application. We're using a tooth belt system directly connected to a servo motor through a servo coupling. On both the left and right sides of the belt, we've installed limit switches. In this setup, the right limit switch also acts as our homing sensor. First, let's demonstrate homing using an incremental encoder. Panasonic servo drives support several homing methods in incremental mode. After implementing the axis in our project, we call the required function blocks to start the homing process. In this example, we're using homing method 18, which performs homing to the positive limit switch. Once the axis reaches the mechanical reference position, in our case the limit sensor, the homing is complete. At this point, the done bit of MC_home becomes true. To make sure the homing data is retained after a power cycle, we save the parameters to the driver's EEPROM. Now let's switch to referencing, using the absolute encoder of the same motor. As we mentioned earlier, no homing movement is required when using an absolute encoder. However, there is one important step during the initial startup. The multi-turn data must be cleared. Absolute encoders provide two types of position data. Single-turn data, the motor position within one mechanical revolution, 0 to 360 degrees. Multi-turn data, a count of how many full motor revolutions have occurred. We parameterize our function block with encoder setting equals 0, which selects the absolute encoder. These parameters are then written to the EEPROM of the servo drive. After that, a power reset is required for the changes to take effect. Next, we perform a multi-turn clear, resetting the multi-turn counter to 0. This step also requires another power reset of the servo drive. Back in the project, the relationship between mechanical position and logical position is now established. From this point on, no homing sensor and no homing procedure are required. So, to summarize, homing finds a mechanical reference by physically moving the axis. Referencing accepts the absolute position directly from the encoder without movement. Both methods serve the same purpose, but the right choice depends on the type of encoder you're using. If you'd like a deeper dive into this topic, feel free to book an on-site or online training session with a live trainer. Thanks for watching, and see you in the next video.
Panasonic Industry